RF. This would be the current that is flowing through the diode. Let me call this as IF. IF would be flowing in the same direction as ID of t. So ID of t would be IF. As we said, the switch is in position 1 from quite some time. We can assume the diode would have reached a steady state where the current flowing through it wouldn't be a function of time. And similarly, the voltage across the diode wouldn't be a function of time. And in general, the voltage across the diode can be taken as cut-in voltage, because in the diode characteristics, if we project this point, we would get a voltage which we usually call as cut-in voltage, V gamma, which would be very close to the built-in potential VBI. Once the applied potential crosses this, the current increases exponentially. So assuming the diode is actually on for this applied potential VF, we can say the potential across this diode would be very close to the cut-in voltage. Now let me plot the current flowing through the diode and the voltage across the diode in two separate plots. When I'm taking the first graph on current potential VF, the applied can be VP and behavior sudden change diode. Let me take this, set that this is position. The VR would take action and VF would be out of the loop. Now let me assume from quite some time the switch is in position 1. In that case, the current that would be flowing in this circuit would be equal to the voltage source VF minus the voltage across the diode, let's say in this case VT of t, over RF. This would be the current that is flowing through the diode. Let me call this as IF. IF would be flowing in the same direction as ID of t. So ID of t would be IF. As we said, the switch is in position 1 from quite some time. We can assume the diode would have reached a steady state where the current flowing through it wouldn't be a function of time. And similarly, the voltage across the diode wouldn't be a function of time. And in general, the voltage across the diode can be taken as cut-in voltage, because in the diode characteristics, if we project this point, we would get a voltage which we usually call as cut-in voltage, V gamma, which would be very close to the built-in potential VBI. Once the applied potential crosses this, the current increases exponentially. So assuming the diode is actually on for this applied potential VF, we can say the potential across this diode would be very close to the cut-in voltage. Now let me plot the current flowing through the diode and the voltage across the diode in two separate plots. When I'm taking the first graph on x-axis as time and on y-axis as the current that is flowing through the diode, and in the second graph I'm taking same time on x-axis, and on y-axis I'm taking potential across the p-n junction diode. This is the t is equal to 0 point. As we said, the switch is in position 1 from quite some time till t is equal to 0. So basically the current that is flowing through it is IF. So let me represent the current on this graph. So this magnitude is IF. How much of a current flows through the diode? The voltage across the diode would be very close to V gamma when it is in forward bias. So I'm taking the voltage across the diode to be approximately V gamma. And now let's say at t is equal to 0 exactly, the switch is thrown from position 1 to position 2. So at t is equal to 0, it is thrown from position 1 to position 2. It says when t is greater than 0, VF is disconnected from the circuit, VR is connected. Now which means VR would be reverse biased in the diode. But immediately after t greater than 0, we want to know how the diode reacts to this situation. But for sure we know if you leave the switch on position 2 for quite some time, the diode would reach steady state in reverse bias. In that case, the current that would be flowing would be simply I0, and that will be in opposite direction to that of the assumed ID of t. So we can say when t is very high, greater than, the current that would be flowing would be simply I0. I'm representing that value of current that flows when the diode reaches steady state, and this would be I0. Assuming I0 is negligible, and the same I0 is flowing through RR resistor, so the potential drop across RR can be neglected, so that the entire potential of this voltage source is applied across the diode. But with respect to the reference VD of t, the voltage would be minus VR. So in steady state, this magnitude would be approximately VR. We have drawn current flowing through diode in steady state and voltage across the diode in steady state. But when we change the switch from position 1 to position 2 immediately and for some time, there is a transition region over which we want to understand how the diode behaves. And that is called the transient behavior of the diode. To understand that, we need to see how the minority carrier concentration distribution is inside the diode for these two steady state conditions. When diode is in forward bias and in steady state, then the minority carrier concentration distribution would look like this, where yellow curve represents the hole concentration on n side and red curve represents the electron concentration on p side. And when the diode is reverse biased and is in steady state, this is how the minority carrier concentration distribution would look like, where again this yellow curve represents the hole concentration on n side, red curve represents the electron concentration on p side. And these graphs are drawn based on the assumption p is highly doped compared to n. We have spent enough time understanding these minority carrier distributions in previous videos, so I wouldn't be explaining them now. Let's say for t less than 0, this is steady state 1. After the concentration distribution should look like this. In steady state 2, the minority carrier concentration distribution would look like this. Now, all that happens between these points for t equal to 0 and this point, the carrier concentrations should change from this to this. In this situation, we know the barrier potential would be VBI, minus width would also be small because the barrier potential is small. Now, in this case, the barrier to the left side would be higher, and there would be a point where VD would be 0. And in that case, we would have VBI and electric field and depletion widths all of p-n junction under equilibrium, which means when it is making a transition from here to here, it basically goes to this state and to this increasing. And now to understand this transition would change with respect to time. Just after t equals to 0 plus, there is no forward bias voltage applied because the switch has been moved from position 1 to 2. There is no external force to have this injection of minority carriers happening. So now what happens is, the electric field in this depletion region is actually directed from n side to p side. And we have seen this electric field would increase as we allow time to increase, which means this electric field would series holes and send them to the n side. As a result, there are a lot of carriers available for the electric field to actually move. The electric field would be moving a lot of carriers across and send them to the n side. As a result, the increase as we allow time, electric field in this depletion region is actually directed from n side to p side. And we have seen this electric field would increase as we allow time to increase, which means this electric field would series holes and send them to the n side. As a result, there are a lot of carriers available for the electric field to actually move. The electric field would be moving a lot of carriers across the depletion region, which means even though we suddenly change it to reverse bias, there would be current flowing, but the direction of the current would change. And as there are plenty of carriers which can actually move, the current wouldn't be limited by how much the diode can supply. Instead, it would be limited by the external resistor RR. So as a result, the amount of current that can flow would be equal to minus VR over RR approximately. And as the electric field keeps taking up the holes, the hole concentration at the edge of the depletion region would decrease and it would become like this. And as time progresses, the electric field would increase. As a result, more number of holes would actually be swept across the depletion region. So the hole concentration would decrease. And at the same time, there are a lot of electrons present on this side because it is N side. The electrons would actually be recombining with them to reduce the hole concentration as well. Now, if we allow time to progress, the hole concentration would still reduce. Even though the carrier concentration is decreasing, which is available for the electric field to move across the depletion region, the electric field is increasing. So now we can see the number of carriers flowing per unit time wouldn't change pretty much. It would be almost constant. So as a result, we can say the current that would flow would be approximately same for some time. And once the carrier concentration would reach this level, that is when basically the diode has come to equilibrium state. In that situation, the potential across the depletion region would be just VBI, which means the potential difference across the PN junction diode as such would be zero, which means VD would be zero. So I'll represent that here. In terms of potential, at this point, potential would be zero. But now as we allow time to change, now the number of carriers available would be very limited, even though electric field is increasing. So the amount of current that would flow will decrease drastically, and the concentration of holes would become like this. And finally, we'll have this concentration which is equal to the concentration for a steady state reverse bias condition. The magnitude of current would decrease and reach this value. And these whole concentration changes would be for increasing of current would decrease and reach this value. And these whole concentration changes would be for increasing time. As time is increasing, the whole concentration would be changing, like concentration to change basically to the concentration for a steady state reverse bias condition. The magnitude of current would decrease and reach this value. And these whole concentration changes would be for increasing time. As time is increasing, the whole concentration would be changing like this. And now if you look at the potential across the PN junction, it wouldn't pretty much change, but once it comes to this point, it changes like this. And once the carriers are not there for current conduction, basically it is allowing the depletion region to increase, and it comes to reverse bias condition. So the potential across the PN junction diode would decrease like this. This time duration over which the stored charge was actually reduced to equilibrium concentration, we call this TSD, representing the stored charge removal time, and the amount of time that it takes since the switching happened to the point where the magnitude of current has come to 10% of the magnitude of the initial current. This time duration is called the reverse recovery time, because the diode is taking at least this much time to actually recover to come to reverse bias condition. And this difference, the reverse recovery time minus stored charge removal time, we would call this as rise time. So an important point to note that even though we switched the potential supplied for the PN junction, instantaneously the diode takes TRR time to come close to steady state reverse bias. Because of the presence of the injected carriers in the forward bias, the diode takes quite a bit of time to actually remove them to actually come to the reverse bias condition. Now, how can we reduce this reverse recovery time? Because obviously, when we apply positive potential, we assume the diode should conduct current, and when we reverse bias, it should not at all conduct current. But it seems that there is a short period of time where it is actually conducting current. Of course, we cannot make a reverse recovery time zero, absolutely, but we can reduce it. Now, what are the parameters by which we can actually reduce the reverse recovery time? So, number one, it is taking time to actually remove the stored charge. What if to start with the stored charge itself was less? Which means if the
What if I told you that something